this video, we're talking about 30, 60, 90 triangles, which are a very special case of triangle. And when we say 30, 60, 90, what we're referring to are the three interior angle measures of the triangle. So if we look at this first figure right here, what we see is that we have a right triangle. We know it's a right triangle because we have this indication here that we have a 90-degree angle in one corner. And then we see that we have two other angle measures, a 60-degree angle measure and a 30-degree angle measure. So this is an example here of a 30, 60, 90 triangle because we have 30 degrees, 60 degrees, and 90 degrees as the three interior angle measures. The reason that this kind of triangle is a special kind of triangle is because it's exactly 1/2 of an equilateral triangle, meaning a triangle that has three sides of the same length. So if we drew in the other half of the equilateral triangle, something that looks about like this. So we have an equilateral triangle where the lengths of all three sides are the same. So when that's the case, what we end up with is a special relationship between the lengths of the three sides of half of that equilateral triangle, the 30, 60, 90 triangle. And the reason is because if you look at this whole equilateral triangle, what you can see is that at the base here, we have the base of the 30, 60, 90 triangle as A. Well, of course, this here is the altitude of the equilateral triangle, and we have this 90-degree angle, which means we're going to have a 90-degree supplementary angle on the other side. And what we can say is that this length here is also going to be A. That means that the total length of the base is going to be A plus A, or 2A. So the total length of the base here is 2A. Keep in mind, though, that this is an equilateral triangle, so the length of the base here is going to be equal to the length of this side, C. In other words, 2A is equal to C, or A is equal to C over 2. What this relationship tells us then is that when we have a 30, 60, 90 triangle, the length of the shortest side is always going to be half the length of the hypotenuse. Or if we take the length of the shortest side and double it, we're going to get the length of the hypotenuse. So this side, the length of this side, the hypotenuse, is always going to be double the length of the shortest side. So we have that special relationship between the shortest side and the hypotenuse. What about this side here, the altitude of the equilateral triangle, or the longer leg of the 30, 60, 90 right triangle? Well, because this is a right triangle, of course, we can apply the Pythagorean theorem to the right triangle. And what we basically need to realize is that C is equal to 2A. So if we adapt here the Pythagorean theorem that we have, knowing that C is equal to 2A, we can make a substitution and say A squared plus B squared is equal to 2A squared, because C, the length of the hypotenuse, is equal to 2 times the length of the shortest side. So then if we simplify this, what we're going to get is A squared plus B squared is equal to 4A squared. If we subtract A squared from both sides, we get B squared is equal to 3A squared. And then if we take the square root of both sides to solve for B, we get B is equal to, the square root of 3 is just, of course, square root of 3. The square root of A squared is A, so we're going to get B is equal to the square root of 3 times A. In other words, we just take the length of the shortest side and multiply it by the square root of 3, and that's going to be the length of the longer leg, the side here, B. So what we can say then about the general measurements of the side lengths of a 30, 60, 90 triangle is that if we call the length of the shortest side A, or we call the shortest side A, then the longer leg is going to be the square root of 3 times A, and the hypotenuse is going to be 2A. So we have this kind of relationship always, no matter what the lengths of the sides of the triangle. We're always going to have this relationship between the side lengths of a 30, 60, 90 triangle. So let's apply that for a second to a couple examples. In this first question here, we're dealing with this triangle, and we've been told that A equals 6. In other words, the length of the shortest side is 6. So what's B and what's C? Well, if we use this relationship here, we know A is equal to 6, B is the longer side. The length of the longer side is always going to be square root of 3 times the shorter side. In other words, 6 square root of 3. And the length of the hypotenuse, C, is always going to be 2 times the shorter side. So we just double the shorter side, so 6 times 2, and we get 12. And just like that, we have the three lengths of the sides of this 30, 60, 90 triangle. What about if we're given the length of the longer leg? So we start with the length here of side B. Well, in that case, to find A, we basically know that 6 is equal to the square root of 3 times A. So if we take 6 equals root 3 times a. We divide both sides by root 3. We're going to get a is equal to 6 over root 3. If we want to rationalize the denominator and multiply by square root of 3 over square root of 3, what we're going to get is 6 root 3, all divided by root 3 times root 3 is 3. And when we divide both the numerator and the denominator by 3, we're going to get 1 here, we're going to get 2 here. That's going to simplify to 2 square root 3. Of course, then now that we have the length of the shorter side, we know that the length of the hypotenuse, c, is just double the length of the shorter side. So what we do is we just multiply the shorter side by 2, and we get 4 root 3 for the length of the hypotenuse. What about if we do this third example here? In this case, we've been told the length of the hypotenuse, and it happens to be 14. So right away, if we know the hypotenuse is 14, the length of the shorter side is always half of the hypotenuse. So we know right away the length of the shorter side is going to be 7, half of 14. And then once we have the shorter side, we know that the length of the longer leg here is going to be the shorter leg times root 3. In other words, 7 square root 3. So that's how we can apply this special relationship between the side lengths of a 30, 60, 90 triangle. As long as we remember this, which only applies specifically to the 30, 60, 90, we can very easily find the lengths of all three sides if we know just one side length. What about if we look at it from a different angle? In this question, we've been asked which of these represents a 30, 60, 90 triangle, and we've been given sets of side lengths. So this first set of side lengths here, we have the three sides of the triangle, 3, square root of 3, and 2 root 3. So the easiest way to go about this is to look for the smallest value. So obviously 2 times the square root of 3 is a larger value than the square root of 3 because it's double that, right? So we know that square root of 3 is less than 2 root 3. And of course we know that square root of 3 is going to be less than 3, which tells us that this square root of 3 value here is the smallest of the three values, which means it has to be the length of the shorter leg. It has to be side A here. So if we're starting with that value, we know that the hypotenuse has to be double this shorter value, which means it would have to be 2 root 3. So we look and we see that we have the hypotenuse here, 2 times the square root of 3. And we know that the longer leg, side B, has to be the length of the shortest leg multiplied by the square root of 3. So if we take square root of 3, the length of the shortest leg, and we multiply it by square root of 3, we're going to get, of course, 3, and that checks out. That is the length of the longer leg. So we know that these three side lengths do, in fact, represent a 30, 60, 90 triangle. If we look at this set of side lengths here, we have square root of 2, 2 square root of 2, and square root of 6. Do these three side lengths represent a 30, 60, 90 triangle? Well, we need to identify the smallest value. So square root of 2 is obviously smaller than 2 times the square root of 2, and it's also going to be smaller than the square root of 6. So we know right away that this is the length of the shortest side. So this has to be side length A. The hypotenuse, side length C, is going to be 2 times this value. So this right here has to be the hypotenuse, which means that this has to be the longer leg. And so if I take square root of 2 here, and I multiply it by square root of 3, which is what I always need to do in order to find the longer leg, what I get is the square root of 2 times 3 when I use my radical simplification, which is the square root of 6. And because that matches this third side length, this checks out, and these three side lengths do in fact represent a 30, 60, 90. Let's do our last example here. We have the three side lengths 2, 1, and 2 square root of 3. We're looking for the smallest value, and that's going to be 1. If you're not sure, you could always do 2 times the square root of 3 on your calculator quickly, but you'll see that 1 is the smallest value here. So in this case, we know 1 is the smallest value. That has to be the length of the shortest leg, the shortest side, or side length A. We know that the hypotenuse has to be double this value. Well, 1 times 2 is 2. This must be the hypotenuse here. The length of the longer leg, side B, has to be this value times the square root of 3. So if I do 1 times the square root of 3, what I'm going to get is square root of 3. But this doesn't match 2 times the square root of 3. It's just square root of 3. So because these don't match, I know that these three side lengths can't possibly represent a 30, 60, 90 triangle. So the important thing to remember here is that because this is a right triangle, you can always fall back on the Pythagorean theorem if you don't remember this special relationship between the lengths of the sides of a 30, 60, 90 triangle. But if you want a shortcut, with the special 30, 60, 90 triangle, which is half of an equilateral triangle, then you can remember that A is the shortest side, the shortest leg of the equilateral triangle, that the longer leg is root 3 times the length of the shortest leg, and that 2 times the length of the shortest leg will always be the length of the hypotenuse.